Welcome back. I just showed you by example how the IDE framework actually works and constructs jump functions for, well, different kinds of call-leaf functions. What I still haven't shown you is what really happens at control flow merge points. So we saw basically merge points that occur inter-procedurally, right? That you have through a return from a given callee, for instance. But you can also have control flows that merge together because you have an if then else, for instance, in a procedure, right? So let's assume here we have a procedure that initializes t to 0, and then there's an if then else, and if you go through the branch, then t is being incremented. Otherwise, if you fall through the branch, then it's not. Okay, so essentially at this print statement, depending on whether you take the branch or not, you can have the value 0 or 1. And this means there's one branch here along which you basically obtain one jump function, but there's another branch along which you obtain another jump function, right? And the question is what happens then? So for instance here, if we want to compute the jump function that leads us all the way to down there, then it would look as follows, right? So we assume we have a jump function that already leads us here, and that is labeled with the constant function 0. And then we have an identity here that is being composed, and we have the increment function. So we obtain this constant function 1. That's what this red edge has to be labeled with, okay? Now we can assume that we want to also compute this jump function that brings us to this node. And similarly, this is being labeled with the constant function 0, right? And now the question is, if we now want to compute a jump function for this node, how is that being done, right? Because essentially we have conflicting information coming from here and from there. And the way it's done in IDE is that, well, you really get these two different jump functions. One comes from the one side and one comes from the other side. And then you somehow need to compose them, right? Or you need to compute a meet operator across them. And this is now a question of analysis design, actually, right? So what do you do here? Now, quite obviously, we have conflicting information, right? And so if you assume that this is a constant propagation that wants to simply compute whether or not you have a constant value, and if so, what it is, then in this case, it might actually make sense to simply replace this by the jump function that maps everything to top, right? Because obviously it's not a constant value, right? Depending on where you come from, it's either 0 or 1, so it's certainly not constant. And top could be chosen to represent exactly that. Other choices might be to actually choose for the value domain here, for this right-hand side, an interval domain, right? So we could have an interval instead. So we could have a function that maps I to the interval between 0 and 1, for instance, right? That would be another design choice. But essentially, you have to implement exactly such reductions. And yeah, talking a bit more about how to actually implement concrete instances of the IDE framework. So when you are instantiating an IFDS problem, for instance, using a program analysis framework such as Suit, and we also have an IFDS implementation based on Suit that is called Heros, then Heros will ask you to actually define flow functions and a lattice, right? So the lattice is essentially your abstract domain that is used to label the nodes with. And the flow functions, they tell the IFDS framework how to create edges for the extended supergraph nodes or exploded supergraph nodes. Then for IDE, you have to define more. So you have to define also the edge functions, right? So for each flow function that is being created, you need to tell the framework what edge function that particular flow function should be labeled with. And then you also need to define a merge or meet operator for the edge functions. I showed you that when I was telling you, for instance, yeah, on the last slide, right, how two different edge functions should be merged together. And importantly here, you can have a non-trivial merge function, right? So this does not have to be union, right? So you can do things like I showed you on the previous slide. You can say, I'm jumping to top. You are not bound to say, I'm collecting all these stupid numerical values that are not going to be helpful to me anyways, right? So you can have a reduction here, and therefore, in many cases, you should also make use of this. Then also, of course, you need to have a composition operator for the edge functions, right? That's probably also very essential, right? Because like I showed you, there are many of these edge functions that need to be composed together. And so in that sense, IDE is really an extension to IFDS, right? So any IFDS problem, in fact, is also an IDE problem. And if you look at our Hero solver, for instance, it's also implemented this way. But in fact, this idea that I'm showing you here, you already find in the original IDE paper. So basically, there is a way to encode an IFDS problem as an IDE problem. So that means if you want to solve an IFDS problem, but you only have an IDE solver, it's no problem at all, right? So you can simply instantiate the problem like I'm explaining you here, and then you can just solve it using the IDE solver. And the idea is basically that in such an encoding, you simply use a very simple binary domain as your value domain. So this is the domain or letters that you choose to label the edge functions with, or functions over the edge functions with. And then essentially, you are talking about such mappings here, right? So for instance, if you have such a mapping here that maps A to bottom, B to top, and C to bottom, it really represents the information that at this point, B is reachable. Okay, so by setting something to top, you're saying that it's reachable at this program point, whereas A and C are not reachable. Okay. And then you can simply define a merge function that looks like this, or a meet operator that's basically saying that something is unreachable if it's unreachable on both sides, right? And otherwise, if it's reachable just along one of the two incoming control flow paths, then it's reachable, right? And if you look into our Heros implementation, it's exactly done like this, right? So if you ask Heros to solve an IFDS problem, then Heros will actually delegate this to an IDE solver that is just parameterized using such a special binary domain. And sometimes students also ask me, okay, but why is this framework actually called interprocedural distributive environment problems? Where are the environments? And you may not see this at first if you only think about this in terms of these micro functions and the jump functions and how they are labeled with these edge functions here. But you can see the environments if you think about how analysis information is really transformed from one statement to the next. So if you see this entire construct here as a function that transforms information, data flow information that you have before the statement into data flow information that you have after the statement, then this whole thing can be described as an environment transformer. Why is that? Well, essentially here you could have an input environment, right? That says at this program point, I have a mapping from A to 0 and B to 2. So that's your input environment. And then if you apply this environment transformer here, so the really the combination of these different microfunctions, then the result is another environment, right? Where A points to 0 and now B points to 1 because B has been assigned this 0 plus 1. Okay. So we have just transformed this environment into another, and therefore this whole this whole flow function as it is, or transfer function, that's really one environment transformer. And in particular, it's a distributive environment transformer, right? So that's why you have interprocedural distributive environment problems. And like I explained before, I put this finite in brackets here, right? Because, well, if you think about it, the right-hand side here, right? So this lattice L that is responsible for the value computations in this case, that can be infinite, right? Because, well, essentially here we are not computing a fixed point over this anymore. We're simply computing the numerical effects as a side effect of following the flow function computation, right? So can actually really be infinite. But this domain D here, which in this case we use to encode these variable names, so this is for the context independent information, this still needs to be finite, right? Because you still need to have a finite number of nodes in order to have termination here. But there's still a very nice property about IDE, and I really cannot emphasize this enough. So recall that IFDS has this complexity here, okay? So we are cubic in the size of the data flow domain. And we said that this is a problem if D becomes large, okay? Now in IDE, we essentially decompose this domain D into two domains. So we still have a domain D that is used to label the nodes, but the context-dependent information we are factoring out into another lattice L, which is basically a value domain, right? So in Sood or Heros, I actually also called it V, not L, if you look at the documentation, because it's essentially a value domain, right? It describes the values that you are computing along these edge functions. And so this is being factored out. And now the interesting part is, and I find this really exciting, that the complexity of IDE is also still the very same, it has still the very same bound, right? So this is exactly the same expression, only that D now, it's a different D, right? So this is smaller now. So if we had to encode constant propagation in IFDS, then D would here be the domain of pairs of variables and numeric values, right? But here, D would only really carry the variable names and no numeric values any longer. And obviously the set of variable names, it's very finite. And if you look at what variable names are really used within a single procedure, then you will see that within a single procedure, these variable names are very, very finite. So it's typically a very small set you're talking about. So actually, by factoring out the numeric values into L, which can even be, an infinite set now, really the complexity of the whole problem, it shrinks immensely. So you get a solution that is a lot faster, and simply because now, you have a lot better summary reuse, and basically the whole fixed point computation is only defined in terms of D, and so also the termination only depends on D. And the numeric values, or in general, anything that you compute in L, that is only being computed as a side effect. Now, there's one other thing that I would like to discuss, and this is that you should be aware of non-distributive operations, and they can really be causing a bit of trouble. So when I was talking about constant propagation in the last couple of lectures, I was always talking, for instance, about the distributive variant of it, which is called linear constant propagation, right? And I told you in linear constant propagation, you have this case that basically one numeric computation, it's always only depending on a single numeric value, not multiple of them. Because if you have an equation such as A equals B plus C, so you have one data flow value depending on two others, then you immediately have the situation that you go into a non-distributive problem, which cannot really be modeled precisely in IFDS or IDE. But what I want to show you today still is that you should not be too careless, because you can also have situations of non-distributivity even when you are depending on only a single value here. And so this is actually something that came out of a discussion I had with Uday Ketka. So thanks for pointing this out to me. So here we actually have a situation as follows. We have a modulus operation, right? So this is taking the modulus 2 of the input parameter x. And now here let's assume that we have the value 1 coming from the left-hand side and 3 from the right-hand side. Then, if we first apply the flow function, right, then we can get these different results, or actually we get the same result. That's the important point, right? So x modulo 1 brings us still 1, and x value 3 modulo 1, 3 modulo 2, right, gives us also value 1, right? So we get the same modulus on both sides. So that means if you first apply the flow functions and then merge together, you get a very precise result, right? You get the result that y is 1. It's definitely 1 after applying this modulus operation here, right? Irrespective of which branch you have taken, y is definitely having the constant value 1. Now, if you look at IDE though, you will see that this is not quite what we are getting. So with IDE, we would here get the constant function 1, and here the constant function 3. So far, so good. But now we would merge these functions together before actually applying the flow function. So in IDE, as in basically all data flow frameworks that I know, we are merging before control flow merge points, right, or at control flow merge points. So it's really done before this flow function is being evaluated. And now the effect is the following. So here we would get this data flow function that you see here, right? So it could tell us, okay, I is now being replaced by its modulus to the number 2, okay? But the problem is now that here at this merge point, we somehow need to merge together these two constant functions, right? And well, if we look at this, we have the same situation we had earlier, right? So here we have one control flow branch where we have the constant function 1, and the other one where it's 3. And now essentially we need to merge that to something like top, right? So that's essentially the function that maps I to top. And we now lose precision, right? Because once this is top, then we can apply this flow function here, okay, but it's still going to, the value is still going to stay top, right? So we will never again obtain this precise answer that y is actually definitely 1 after the statement. And that's just a limitation of this framework, right? So that's exactly why IFDS and IDE actually demand that you have a distributive problem. So if you have a problem that is distributive, then by definition you cannot have these losses in precision, right? That just cannot happen. But if you have a non-distributive problem and that happens to be 1 here, then exactly you can see these effects here that you are forced to approximate. Now, last but not least, I want to explain again what the advantages of IFDS and IDE are over the Vasco framework that I explained earlier. I'll be doing that after a short break.